Hi, I'm James. I'm from Cardiff University School of Engineering. Apologies for not being there in person. Some lovely Brexit-related complications at the border of Austria. Today I'm going to talk about some results from our latest paper to answer the question, do microplastics and natural sediments saltate similarly? So my research looks at the differences or similarities in the behaviour of sediments and microplastics that are being transported in rivers. So microplastics and sediments are similar in size. Microplastics occupy the grain size distribution of sands and silt sediment. And they're also similar in terms of their distribution. They can both travel in rivers as bed load, travelling in the near bed region, and suspended in the suspended load region in rivers. However, they are different in terms of their density. Sediments are mostly non-buoyant and sink in water, while plastics and microplastics can be non-buoyant and also buoyant, so they can also float in water. They're also different in terms of their shape. Sediments are mostly rounded or angular in shape, while microplastics can be found as fibres, films, foils, and irregular shapes as well. They're also different in terms of their physical material characteristics, in terms of elasticity, compression, tensile strength, as seen in the table below in terms of their Young's elasticity modulus. Quartz sediment has a much higher Young's modulus than some common plastic polymers. So this is the focus of our latest paper. It would be expected that particles with different elastic properties, like sediments and microplastics, to have different bed load transport characteristics in terms of rolling, sliding, saltation, and this is due to different impact kinematics. So it's maybe expected when a particle hits the bed at a given velocity, a portion of that energy is lost due to restitution, and therefore different trajectories may be expected for particles with different levels of elasticity. Therefore, we wanted to answer the question, how will the bed load transport of microplastics differ when compared to sediments? Are they transported in a similar way? So to answer this, we released microplastics and sediments one by one into an open channel flume over a range of flow conditions and bed roughnesses. We ensured that particles were in bed load transport, and we particularly looked at saltation as their mode of transport in bed load. We chose 3 different spherical plastics with different densities in sizes 3mm and 5mm. We also used amber, we used as a proxy for sediment because of its low density, but also because of its similar mechanical properties to sediments in terms of elasticity. We then video recorded the saltation of both the plastics and the amber to characterize their saltation behavior. The videos here show the video recording of the high-speed camera looking at particles saltating as bed load in one of our open channel flumes, and then we show the particle tracking algorithm used to characterize the saltation motion. So here are some of our results. Figure A shows in average terms the dimensionless saltation length. So this is the length of a saltation jump. So figure B shows the saltation height. This is how, in average terms, how high the particle was saltating. And C shows the saltation velocity over the flow conditions and bed roughnesses that we used in our experiments. The coloured points on these graphs indicate the different microplastics that we used in experiments. We used PA, CA, and POM with different densities. And the different shapes on the graphs indicate the different bed roughnesses we used. In the black points are the amber particles, which we use as a proxy for sediment. And on the x-axis is the Rouse number. So this is the Rouse number calculated as the ratio between the settling velocity of the particle and the shear velocity of the flow conditions that we used in the experiments. And what we find is that the Rouse number could describe both the microplastics and amber equally, no matter what their elasticity of the material was. So no matter whether the particles have more elastic collisions or not, their trajectory characteristics could be well described by the Rouse number. We also look at the distribution functions for each of the characteristics. So figure A, B and C show the kernel density estimates of each of the trajectory characteristics in terms of, again, saltation length, height and velocity. We wanted to investigate whether the distribution functions for microplastics and sediment trajectory characteristics could be drawn from the same functions. So to do this, we fitted a Gaussian and a gamma function to the data. We used Gaussian because we wanted to see if data falled equally between the mean, and gamma to incorporate long tails, and because to incorporate long tails and extreme values, and also because data should be bounded to 0. We then used a Kolmogorov-Smirnov test, a statistical test, to identify whether the sampled data is drawn from either a Gaussian and or a gamma function. So the results of that KS test are shown in figure D, indicating where data was consistent with either a Gaussian and or a gamma function. So this can be kind of seen as a similarity matrix in which the points in the same cell indicate that similar probability density functions could be used for that characteristic at that flow condition. And what we find is that overall there was only one amber case which was potentially drawn from a different distribution compared to all the other microplastic distribution functions. We also look at the collision characteristics of the particles. Figure A shows the average inwards collision angle, so this is the angle at which the particle hits the bed during saltation. And figure B shows the average outwards collision angle, the angle at which the particle leaves the bed after collision. On the x-axis is the Rouse number. Again, we show that the Rouse number is non-discriminatory between sediments and microplastics and can describe both materials' collision impacts equally, no matter what their elastic properties are. So indiscriminatory of whether a particle is plastic or sediment, the Rouse number could describe their collision angles equally. We also undertook a very similar analysis to the previous slide to see if the distribution functions of the inwards and outwards angles for amber and microplastics are drawn from the same functions. We find that only 9 amber cases, so 9% of all the experiments that we did, were different to the microplastic distribution functions. We also look at particle restitution, which is the representation of the energy lost or gained by the particle at collision with the bed. Figure A shows restitution in the streamwise direction, where it is shown that energy is lost at collision as values are below 1. Figure B shows restitution in the vertical direction, where energy from the streamwise direction is transferred to the vertical direction, therefore restitution values are above 1. Representation that energy is gained in the vertical direction. Figure C shows both the streamwise and vertical vectors together as magnitude, where we show that overall energy is lost at particle bed collisions. We find that statistically, using an ANOVA statistical test, that microplastics have significantly lower restitution values compared to the amber sediment, which suggests that microplastics lose more energy per successive collision during saltation compared to the amber particles, which have a higher Young's modulus and therefore have more elastic collisions. Nonetheless, the differences we find in restitution between microplastics and sediments are observed to have no effect on the saltation characteristics of the particles, as seen from the previous slides in terms of the saltation length, the saltation height, the saltation velocity, the saltation collision inwards and outwards angles. And this is because the kinetic energy from turbulence in the flow outweighs the energy that is lost at collision. Therefore, this leaves the particle trajectory characteristics independent of impact. So the key notes to kind of take home are that spherical microplastics behave similarly to spherical natural sediments when travelling as bedload in rivers. The Rouse number can be used to characterise saltation regardless of the material, regardless of whether the particle is plastic or sediment. And therefore, sediment transport theory could be used as a foundation for microplastic transport. Thank you very much for listening. Please feel free to contact me with any questions you have regarding the paper or the presentation here. I'd be very happy to answer them. Thank you very much.